Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you, Anna, and good morning, good afternoon, good evening to everyone. Thank you for joining this webinar organized by the ITU, the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technology. Today, we are looking at AlphaDev, the recent paper by several authors from DeepMind on discovering faster sorting algorithms with reinforcement learning. AlphaDev builds on AlphaZero, the AI system that has demonstrated superior proficiency in games like Go, chess, and Shogi. AlphaDev is a variant on this, which focuses on a unique single-player game aimed at discovering the fastest possible sorting algorithms. And it has surpassed human-designed algorithms in that. It has also been incorporated in the C++ standard library and others, some of the key libraries used by computers around the world. In addition to this, AlphaDev has discovered a faster hashing algorithm. So beyond just a sorting algorithm, also a hashing algorithm, another vital computer process, which has also been integrated in the core computer library. And the authors estimate that these faster algorithms are used trillions of times per day. Today, we have the privilege of welcoming Daniel Mankovic and Andrea Michi, the two of the authors of the paper. Daniel Mankovic is a staff research scientist at Google DeepMind and works on bringing reinforcement learning algorithms to real-world applications at scale. He has worked on reinforcement learning from human feedback, RLHF, in the context of large language models, LLMs, and has also worked on code optimization, code generation, video compression, recommender systems, and controlling physical systems such as heating, ventilation, and air conditioning, or HVAC systems. And he has published his research in journals such as Nature and Science. Andrea Michi is a senior research engineer at Google DeepMind. He also works on reinforcement learning applications and has worked in the past on renewable forecasting, code optimization, and the control of physical systems, such as the magnetic confinement in a tokamak generator. More recently, Andrea has focused also on RLHF, to align large language models to human preferences. And with that, I'd like to give the floor to the speakers.
Hi there, thanks so much for having us. I'll just pull up the presentation. So thanks everyone. And today, as Bastian mentioned, we will be talking about AlphaDev, our algorithm that discovered these faster sorting algorithms using deep reinforcement learning. We'll start by just giving an outline of the talk. So we'll talk first about the motivation of why we started the project and how we came about to optimizing these algorithms. We'll then talk about things like the assembly game, how AlphaDev essentially plays to discover these algorithms. We'll introduce key aspects of AlphaDev, talk about the sorting results and analysis. And then we'll talk a bit about the hashing, motivation for why we chose it, analysis and results of it, and some concluding remarks and thoughts. So Moore's law is coming to an end, and chips are starting to reach their fundamental physical limits. And as a result of that, we need to find new and innovative ways to optimize the computing stack. One such way is to optimize the code that runs on it. Now, we believe that there are many non-trivial and or unintuitive optimizations that exist that we might be able to discover. And this was a lot of the motivation as to why we began this project. And so we asked ourselves at the start of this project, What if we could automatically optimize the world's code using reinforcement learning, potentially discovering entirely new algorithms along the way that can both influence how researchers and practitioners think about, design, and implement algorithms? But the question is, where do we start? Well, we wanted to start by optimizing algorithms or learning to create algorithms at the assembly instruction level, the CPU instruction level. So on the left-hand side here is a program that's been written in C++, an algorithm called variable sort2 that can sort up to 2 elements. Now, what typically happens is this algorithm written in C++ is compiled to assembly, which you can see here in the figure on the right. And assembly is an equivalent program to the C++ variable sort2, and it executes its instructions, as they're called, line by line. So an example of an instruction here is this move instruction that moves a value from a register EAX to a register EDX. Now, assembly algorithms involve manipulating values between memory and registers and outputting the same result as what the C++ algorithm would output. And the reason that we chose to optimize at the assembly level is there's a lot more flexibility at this level. And you're essentially, hopefully, able to find hidden optimizations that you wouldn't have been able to find necessarily in higher level languages such as C++. So we wanted to start with a large fundamental algorithm that is used ubiquitously around the world and is really key to many of the things we do every day. And sorting algorithms struck us as being a really good starting point. So sorting algorithms date back thousands of years to the times of the Great Library of Alexandria, where Zenodotus would be sorting books in the library, to the late 19th century, where you had tabulation machines that were sorting votes during elections. And more recently, sorting has found its way into many different applications, such as information retrieval, job scheduling, information display, recommendation systems, and string processing. And in addition to that, it's a fundamental algorithmic challenge in computer science that has been worked on for many decades. And as mentioned, we estimate these algorithms, or sorting algorithms, are called trillions of times every day. And so by improving these fundamental algorithms and hopefully incorporating them into libraries, open source libraries that are used by developers, companies, and users around the world, we could really have a large impact as a result. So how did we create a way to generate these sorting algorithms that were faster from scratch? Well, the first thing is we formulated solving this problem as a reinforcement learning problem. So for those of you that are unfamiliar with reinforcement learning, here is sort of a primer. So reinforcement learning typically consists of an agent and an environment. And so if we look on the right-hand side, this will sort of be the running example for this slide. There's a Mars rover, which is the agent, and the agent is moving in an environment. So it's moving on Mars in this example, and its goal is to reach the silo, which you can see in the distance. Now, the way the reinforcement learning loop works is the agent starts in a particular state, ST, which in this case corresponds to its XY location. The agent, which is the Mars rover, then chooses an action, where the action could be moving in any of the possible directions to get to the silo. The agent then executes the action and transitions in the environment to a new state, ST+1. So this is the Mars rover selecting a direction to move in and then moves to a new XY location. And then it receives a reward, which in this case could be a negative reward for every step it takes to try and get to the silo as quickly as possible. So this is the general setup. We have a state space, the set of all possible states, which in this case are XY locations, the action space, the set of valid actions, which in this case are the different possible directions for the rover, and the reward of penalizing or rewarding the agent, which in this case are these negative rewards to get to the silo as quickly as possible. And then we have what we call an episode, where this is a trajectory where the Mars rover starts in a state, in a location, takes an action, moves, receives a reward, transitions to the next state, and so on. And the goal in reinforcement learning is to learn a policy, this function pi, which, given the current state, determines what action should be taken in order to maximize the rewards that it gets. And so in this case, the agent, the Mars rover, wants to be able to learn a function that tells it in what direction to move to get to the silo as quickly as possible. So how do we translate this to discovering assembly algorithms, and specifically in this case, sorting algorithms? Well, we defined what we called the assembly game, where here the state space is the algorithm that the agent AlphaDev, or the player AlphaDev, has generated thus far. And remember, all of these algorithms that AlphaDev generates are generated from scratch. So it starts with an empty buffer, and it has to iteratively build up these algorithms, instruction by instruction. So understanding what algorithm you've built thus far is really important to understanding the state of the system. In addition to this, the state of the CPU's memory and registers are also important, because these are getting manipulated by the algorithm that's being generated. And so the state really is comprised with understanding the algorithm that is being generated, as well as how it affects the dynamics of the memory and registers. The action space in this case is the set of valid assembly instructions that it can add to the algorithm, and the reward is a combination of the algorithm's correctness as well as the speed of the algorithm, its latency. So the way this game works is that AlphaDev, the player, receives the state as input. It then selects an action. So in this case, in this example, it's chosen a move instruction to move a value from register 0 to memory location 1. And this then gets added to the algorithm that it's built so far. So now we need to be able to reward the agent now that it's generated a new addition to the algorithm. So the first step is to determine the correctness and reward it accordingly. So if we're, for example, trying to build a sorting algorithm that can sort 3 elements, the idea is that we want to input a set of test sequences, which in this case are the different combinations of 3 values that are input into the algorithm. All of these sequences are input into the algorithm to generate their corresponding outputs. And these should then match an expected output, which for the case of sorting means that whatever sequence you feed in should be sorted when it's output. So we can then reward the agent for the sequences that it sorts correctly, and we can penalize the agents for the sequences that it sorts incorrectly. Once the agent has discovered a correct sorting program, then the agent begins to optimize for latency. Now, latency can be optimized in different ways. For example, if you have a program or an algorithm that you're building where there isn't branching. So this means branching is typically where you have an if-else statement. So if something happens, do this, else do something else. If you have branching, if you don't have branching, then what we find is typically there's a correlation between the length of the algorithm and its latency or its speed. So longer algorithms tend to be slower, shorter algorithms tend to be faster. However, when you have branching and you have if-else statements, things become a lot more complex. And there you don't have these correlations of shorter algorithms necessarily mean faster ones. And in this case, it's critical to optimize for actual measured latency. So how did we do that? This was one of the key contributions of our work. This is something that was really fundamental to being able to discover these faster sorting algorithms. We needed to find a way to measure latency, but there are many problems that come with measuring latency. For example, there's a lot of noise associated with the latency measurements that you get. You can imagine that you're trying to measure the latency of an algorithm, and then some process that's unrelated to your system interrupts it and then causes a spike in the latency, making the measurement useless. So we needed to find a way of generating as noise-free latency measurements of the algorithm as possible. And not only that, we were measuring the latency of fairly short algorithms. And so we had to be able to measure latency accurately on the order of nanoseconds. So to do this, we built what we call the latency benchmarking server. This is a set of machines that were separate from the main training of AlphaDev whilst it was playing assembly game. These separate machines, every time we wanted to process the latency of an algorithm, would process 1,000 measurements across all of these machines. And for each measurement, it would process 10,000 random inputs. We would then take the distribution of these latency measurements and take the top 5th percentile in order to remove as much of the noise as possible. The way in which we measured latency was using a CPU performance counter called the CPU clock unhalted core. And as a result, our server is capable of measuring changes in latency on the order of nanoseconds. So this meant that we could really optimize for actual measured latency. So how hard is this assembly game to play? Well, AlphaDev is building these algorithms from scratch, starting from an empty buffer, which means that in order to build a function such as a sorting algorithm, it needs to be able to consider the combinatorial space of assembly instructions when building the algorithm. Now, the size of this space is similar in size to the number of atoms in the universe, the number of games in chess, and the number of games in Go. And what makes this even more difficult is that a single incorrect instruction can invalidate the entire algorithm. So we really needed to have an efficient way of being able to explore this massive combinatorial space. And to do that, we developed AlphaDev. So AlphaDev, as Bastian mentioned, is an extension of AlphaZero. But there were two key components that we had to incorporate into AlphaDev in order to make this work. The first one was the representation, and we created what we called an assembly transformer. Now, an assembly transformer, if you look at figure A, receives as input the program or the algorithm that's generated thus far as a list of the program instructions that AlphaDev has selected. These get then fed into a transformer encoder, which generates an embedding of the algorithm. This helps AlphaDev to understand the structure of the algorithm. In addition to that, we also keep track of the state of memory and registers. And these are then fed into a CPU state encoder, which is effectively a multi-layer perceptron of a number of layers. This then generates embeddings of memory and registers. And we then combine these together. So this allows AlphaDev to understand how the structure of the algorithm that it's building affects the dynamics of memory and registers that are being manipulated. In addition to this, we devised what we called an assembly latency value function. So evaluating a program's latency is expensive, and we can't do this every time AlphaDev generates an algorithm. AlphaDev runs Monte Carlo tree search, which is a way of generating tens of thousands of candidate algorithms. And to be able to measure the latency, the actual measured latency every time, is just too expensive. So we needed to find a way to be able to get it to predict the measured latency and to do that really accurately. So what we did is, whilst AlphaDev was playing assembly game, we created a bunch of actors that were copies of AlphaDev, whose job was to simply generate assembly algorithms. And every time these actors would generate assembly algorithms, we would compute the actual measured latency each time an algorithm was generated. If you take into account the number of algorithms these actors were generating relative to the number of algorithms that AlphaDev generates in general through its Monte Carlo tree search procedure, we only had to measure the actual latency on 0.002% of generated programs. This meant that we could really efficiently utilize data of the latency measurements for the algorithms that AlphaDev was generating and use it to predict latency. We would then take these measured values from the actors, and we would use that to train the latency value function head. And then during these very expensive procedures, such as search, instead of computing the actual measured latency, we would be able to estimate the latency of a program, even for a partial program, by using this latency value function. So now that we had all the mechanics in place, it was a question of, well, we want to focus on sorting algorithms, but what are the fundamental algorithms that we want to try and improve in the sorting domain? And when we were looking in the C++ standard sorting library, we noticed something very interesting. When you call these libraries, or at least this library that we focused on, and you call sort of 1000, so your application needs you to sort 1000 elements. What happens is typically an algorithm called merge sort is called, that breaks your sort of 1000 elements down into two sorts of 500 elements. And then for each of those breaks it down into a sort of 250 elements. And this becomes progressively smaller and smaller until you start calling sorts of 3 elements, 4 elements, and 5 elements, or sort 3, sort 4, and sort 5 as we call them. So the idea, what we realized is that if we could find a way to optimize and speed up these fundamental algorithms of sort 3, sort 4, and sort 5, not only would they improve sorting elements of that length, but the hope is that they would improve all sorts that were larger than sort 3, sort 4, and sort 5, because these algorithms get called repeatedly. In addition to that, we also wanted to test variable sort algorithms and see if we could optimize those. So variable sort 5, for example, is a sorting algorithm that can sort up to 5 elements. And so the idea is that here you have things like branching, which makes it a lot more complicated, where if, for example, you get a vector of 3 elements, you need to say if the length is 3, then call a sorting algorithm to sort 3 elements. If the length is 4, call a sorting algorithm to sort 4 elements, etc. So we really wanted to test both of these different setups. So the state of the art for these small fixed sort algorithms, such as sort 3, sort 4, and sort 5, are sorting networks. These generate conditional branchless assembly code. So it's assembly code that is fast, that can be parallelized. And so these really do exhibit really good performance and are considered the state of the art. If you look at the figure in figure A, for those of you that aren't familiar with sorting networks, a sorting network consists of horizontal lines, which we call wires, and vertical lines, which we call comparators. And the idea, if you look at figure B, is that if you feed in a sequence of numbers, for example, 2, 3, 1, and 4, these numbers move across the wires, and when they reach a comparator, for example, the first comparator connecting wires with the value 2 and the value of 1, the comparator compares these numbers and then puts the smaller number on the higher wire and the larger number on the lower wire. And as you feed these numbers through the sorting network, they're then sorted at the end. And so this is the visual representation of these sorting networks that can be written as conditional branchless assembly code. So when we started the project, we thought, let's try and take AlphaDev and try and learn, generate from scratch a sorting function that can sort 3 elements, sort 3. The state of the art, when you look at the assembly, is 18 instructions for sort 3. It's a very short program comparatively. And when we looked at it, you know, we're not assembly experts, but to our analysis, we couldn't see any way to improve it. So we thought, let's just treat this as a baseline. Let's try and match this performance. And then as we do larger and larger sorts, hopefully we will find some improvements. But to our surprise, AlphaDev was able to discover a 17 instruction sort 3 program from scratch. We were really surprised by this. We initially, as you often do, think that there's a bug and there's something wrong. But upon analyzing this program, we found that it actually did find a way to reduce the length of the program by an instruction. And when we then looked at the programs, so the left program is the original sort 3 algorithm written in assembly, the 18 instruction algorithm, and the right-hand side is the one discovered by AlphaDev. We found that this instruction number 15, this move instruction, was actually not needed. And so then we wondered, well, is there some kind of structure to what it's learned? Is there something more general to what it's learned? Or is this sort of a one-off? And upon further analysis, we realized that it discovered something more general, which we call the AlphaDev swap move. So the AlphaDev swap move is a move that can be played by AlphaDev, or you can think of it as a sequence of assembly instructions as the move that can be played by AlphaDev when it encounters a sorting network with a particular structure. So if you look at figure A here, there are 3 wires, wire A, wire B, and wire C. Now, if you move along the wires, you'll encounter a comparator that compares wire B and C. And so after moving past that comparator, you've already got guaranteed that the value in wire B is less than the value in wire C. And you can see this in the visual example we have on the right, where if you feed in numbers 2, 3, and 1, after 3 and 1 pass through the comparator, you're guaranteed that the value on wire B and the value on wire C are sorted. Now, if that's the case, what this means is that if you have 2 comparators after that have the structure in this red circle, then you're able to apply the AlphaDev swap move. So in the paper, there was a bit of confusion as to what exactly we were showing in figures B and C. But figure B here shows that after that comparator where you guaranteed that B is less than or equal to C. So you can see here we already have 2, 1, and 3. So 1 is already smaller than 3 on wires B and C. We then showed the program in figure B for the original sorting network that has these 2 comparators with this particular structure following it. So this is sort of the continuation of the program after this assumption has been met. In figure C, you see the same thing for these 2 comparators, except in this case, AlphaDev, when generating the sort3 algorithm from scratch, was able to discover that it didn't need one of these instructions. And this was the AlphaDev swap move. And so we then said, well, let's try and apply this to other sorting functions. Let's go bigger. And so for sort4, we ran AlphaDev, and from scratch, it managed to learn a sort4 state-of-the-art sorting network, which is 28 instructions long, so it matched the state-of-the-art. And for sort5, it managed to learn a function, an algorithm that was 42 instructions long, which is 4 instructions shorter than the human benchmark for sort5 of 46 instructions. What we also found is that AlphaDev learned a 43 instruction program for sort5, 3 instructions shorter than the human benchmark. And what was really interesting about this is that it learned to apply, when generating the sort5 function from scratch, the AlphaDev swap move 3 different times. And it was this sort5 function that we ended up using when we submitted our sort3, sort4, and sort5 algorithms to the C++ library. When we were optimizing or trying to learn a sort8 function from scratch, which Andrea will talk about a bit later, we found that if the assumption holds that the value on wire D is greater than or equal to the minimum between the values on wire A and wire C, and then you have the following structure that follows, you can apply what's called the AlphaDev copy move. And the idea, again, is figure E contains the original continuation of a program where this assumption already holds, so where the values in wire A, B, C, and D fulfill this assumption. And the figure F shows AlphaDev, where you can see it's been able to remove the move PT instruction. So this, again, is another general move that is able to be applied wherever the structure occurs. So we then took our sort3, sort4, and sort5 algorithms that AlphaDev discovered. We reverse engineered them back to C++. And we thought, let's try and submit them to one of the standard C++ sorting libraries. And when we did this, we honestly didn't expect the algorithms to be accepted. We thought that we would learn a lot from the process, but there must be something that we maybe did wrong or didn't think about. But amazingly, after 3 months, we wrote lots of unit tests. There was lots of back and forth to make sure that these algorithms worked as expected, but they got accepted and they were officially integrated into the LLVM libc++ standard sorting library. It's the first change to these subroutines in this library in over a decade. And the improvements that we gained over the functions that existed in this library ranged from 70% for sort5, for sorting 5 elements, all the way up to approximately 2% improvements in speed for sorting algorithms of 250,000 elements and more. And so what was really interesting about this is we had that initial hypothesis that hopefully by improving the speed of the fundamental algorithms, sort3, sort4, and sort5, we would improve the speed of all sorting algorithms greater than that. And this helped to validate that assumption that we saw these improvements on these large sorts as well. This was also the first time that automated code generated by RL has been added to the C++ standard sorting library. And we estimate that our routines are being used trillions of times every day. And you can see some of the users at the LLVM user base, which consists of many international companies, millions of developers, and essentially billions of users. So we then said, well, let's tackle variable sort algorithms. And let's see how AlphaDev does here when trying to generate these from scratch. This is a very difficult problem to do because AlphaDev starts again with an empty buffer and needs to build an algorithm that can determine when to do branching. So it needs to determine when should I add an if-else statement and where should I generate the subroutine that I'm branching to. So we initially started by optimizing for program length, and we found that AlphaDev was able to create significant reductions in the program length or in the length of these algorithms. We focused on variable sort 3, variable sort 4, and variable sort 5, where again, variable sort 3 sorts up to 3 elements, 4 up to 4 elements, and variable sort 5 up to 5 elements. And we found, for example, in variable sort 4, that AlphaDev was able to discover algorithms from scratch that were up to 29 instructions shorter than the human benchmark. And when we optimized for actual measured latency, we found that we were able to significantly improve upon the speed of these human benchmarks as well in each case. So to give you an idea of the types of algorithms that AlphaDev is generating from scratch, this is an example of the fastest variable sort 4 algorithm that it generated. And it's a bit difficult to see all the assembly in this algorithm on the right, but all of these lines from line 414 down to 470, were all generated by AlphaDev. And AlphaDev, if you see, there's jumps on line 417 and 427, and these were the branching bits. So it had to determine when to place a jump statement, and then it would jump to a place further down in the program, for example, all the way to line 436, and it would then need to build a subroutine there whilst taking into account the general structure of the program. And what this meant is that there was actually a lot of flexibility, and AlphaDev was able to discover an algorithm that was fundamentally different from the human benchmark. So the human benchmark for variable sort 4 would be receiving, for example, a vector of 4 elements. If the length of the vector is 4, call sort 4 to sort 4 elements. If it sent in 3 elements, it would call, if there were 3 numbers, it would call sort 3 and sort those. But what AlphaDev learned was something fundamentally different. So in this case, if you send in 4 elements, the first thing it does is it says, well, is there only 2 elements in this vector? And if that's the case, it calls sort 2 and we're done. But if there's more than 2 elements, like in this case, it then goes down and calls sort the first 3 numbers. So it calls sort 3. Then it says, well, are there 3 numbers in this vector? If there are only 3 numbers, then we're done. We've sorted the 3 elements. However, if there are 4 numbers, which is the case here, it calls a much more simplified sort 4 routine that only has to sort 2 of the numbers because 3 of the numbers are already sorted. And it's this type of discovery that allows it to get these significant latency gains as a result. So I'm now going to pass over to Andrea, who's going to take you through the rest of the conversation, of the presentation.
Thank you, Dan. So Daniel gave an introduction to the assembly game and the architecture of AlphaDev, also gave an analysis of the sorting and variable sort discoveries. In this second part of the talk, we will first look at what the baseline and how do they compare against AlphaDev. We will then look at the problem scaling, and then if we can go beyond the sort 5. And we will look if we can generalize to domain other than sorting. And finally, we will talk about some limitations of this work and future work. So in terms of baseline, we really wanted to compare against a strong baseline. So what we did, we implemented a state-of-the-art approach called stock, which is a stochastic search approach, into the same setting that we had, and we call it AlphaDev S. Here we use the same assembly game, the same correctness checking routines, and we give it a like-for-like type of run, so like we use the same amount of resources and clock time. There is one main difference, which is the absence of the latency value function, which of course doesn't fit in AlphaDev S. So there is a strong implication of this. So because as Dan talked about the latency value function, it is what allows us to be very efficient when we optimize end-to-end for latency. Without the latency value function, we are not able to optimize directly for latency. We tried, but it was way too slow. So a mitigation that we use is we optimize for program length instead. And afterwards, we take the K shortest programs. So we take like thousands of programs that are the shortest. We benchmark the latency for each one of them, and we pick the fastest. So this is not exactly the same, but is the mitigation that we used. So how do they to compare? Well, when we compare AlphaDev S and AlphaDev, we observe that AlphaDev outperforms AlphaDev S when learning from scratch without prior knowledge. What does that mean? It means that when both algorithms start from zero, like an empty buffer, and play one instruction at a time, AlphaDev does better. On the other hand, if we give an already sorting program to AlphaDev S, which we call this warm-started setting, where AlphaDev S can remove, modify instructions, or add instructions, in this setting, AlphaDev S does perform very well and is more computationally efficient. And finally, the third observations that we did is as the algorithm size increases, oh, you can do it. Okay, I will do it after the question, sorry. As the algorithm size increases, AlphaDev explores significantly fewer algorithms than AlphaDev S. So for instance, if we look at variable sort tree, AlphaDev S explores 31 trillion programs. This is compared to just 12 million that AlphaDev explores. So with these numbers, we thought, okay, maybe AlphaDev better explores the algorithm space. It's more efficient searching through the space. So we tried to visualize these hypotheses, and we applied t-SNE to the variable sort for algorithms discover. What you can see in the left is the three algorithms, AlphaDev, and then AlphaDev S, both in the warm started and cold started. Where cold started, empty buffer, warm started, we already give a sorting program. It's interesting when we look at AlphaDev S, if you look at the search that it does, it's very uniform. It almost looks like a bubble. And it seems like it does almost a breadth search, right? So it starts from the center and moves in the space, searching very locally. While when we look at the search of AlphaDev, it's a lot more complex. And this complexity becomes a little bit more clear if we do a breakdown by correctness. In the case of the starting from an empty buffer, AlphaDev S cannot find a correct solution, remains only in the space of incorrect programs. While when we look at AlphaDev, it starts from an incorrect program, of course, because it's the empty buffer, and slowly starts to find programs that maybe source a few permutations, and finally goes to programs that source all the permutations, and also fast programs that are correct. So this is how we compared against one baseline. But then the question was like, can we go beyond the sort 5, right? And there are a few scalability challenges here that we'll talk about. So of course, like when we go beyond sort 5, the algorithm size increases. So this introduces a learning problem in terms of like there are more instructions. It's harder for the agents to understand the meaning of each instruction. And we'll talk in a few slides about the assembly graph net, which is a way to address that. Then the biggest problem, though, is the problem of correctness. So right now, in order to verify correctness and give a reward, we run the algorithm on each permutation. And this, of course, doesn't scale really well. And we'll look in a few slides at how we address that with the 0-1 principle. And the third component that we use to scale is that move from AlphaZero to mu0. So for those of you who are familiar with AlphaZero and mu0, the main difference between the two algorithms is how they perform the Monte Carlo tree search. In the case of mu0, the Monte Carlo tree search is done in the latent space. So you have, like when you do the search, you have similar to the latency value function, we also have a correctness value function, and everything is done there. So it's a lot more efficient. Cool, so very quickly looking at the assembly graph nets, the challenge here is that the program size increases, and the intuition is that we already know a lot about these programs, even before we do any learning. So for instance, if you look at the example program below, the first instruction is move memory 1 to register 1. If we represent this program as a graph, we can represent the first memory location as one node, the second, the register location as another node, and the instruction can be represented as an edge from the first node to the second node. Representing these programs as a graph adds some prior information to the agent and makes learning more efficient. Then the second problem is the scalability problem. So as you can see in this table, the number of permutations that we need to check follows what we call the bell order distribution. So there are just 3 permutations for size 2, for sort 2, but for sort 8, there are more than 500,000 permutations. It doesn't scale that well. In the case of the sorting networks that Dan introduced, there is a very nice principle called the 0-1 principle. This principle says that if a sorting network sorts all binary sequences, so all sequences of 0 1s, then it sorts all sequences of arbitrary numbers. This is great because it means that when you have a sorting network, you just need to check permutations of 0 1. So in the case of sort 8, we just need to check 255 permutations. Fantastic. The bad news is that it doesn't apply to us because we have a more complex structures, right? We don't just have compare swap operators, we also have moves, conditional moves, and so on. This principle doesn't apply. So what we did is we represent the structures that we have, which we call assembly sorting network. In this sorting network, we introduce all different moves that we have. We have a normal move, a normal comparison, which is not a compare swap of the sorting network, it's just a comparison. We have conditional moves, and so on. And we were able to prove an extended version of the 0-1 principle, which we call assembly 0-1 principle. And we have the full proof in the paper if you're interested in. But what we were able to prove is that if we respect one condition, then the 0-1 principle also applies to the assembly sorting network. So what's this condition? Well, it's very simple. It says that whenever you have a conditional move, it must be applied to values that fall within the range of the previous compare operation. So if you look at the red box, we have 2 conditional move less. And then if you can see, they're applied to the same wire of the first operation, which is a compare operation. If that condition is respected, then we can just check permutations of 0 and 1s. And that really restricts the number of permutations we need to check. And it's really what allows us to scale up to sort 8. Of course, there are different ways to scale to larger sorts. We don't really have to check every permutations. Like one could think of maybe you can sample some permutations and so on. But at some point when you want to verify the correctness of the algorithms, you're really forced to check. Unless you go into formal proving, this is the only option you have. So how does it perform beyond sort 5? Well, we tried in sort 6, and we're really happy to discover that a 57 instructions program, which is 3 less than the baseline. In sort 7, we discovered a program with 2 instructions, that saves 2 instructions. And finally, in sort 8, we were able to save 1 instruction. So this was really good news. But then the bigger question was okay, we can scale to beyond sort 5, but can we generalize to other algorithms other than sorting? And if there is an algorithm that is maybe as famous as sorting, it has to be hashing, which has been around for more than 70 years. It was invented by Hans-Peter Lohn. Initially, the idea behind hashing was to bucketize information in order to speed up search. But nowadays it's used pretty much everywhere, right? From information retrieval, and it's a key component of data structures like hash maps. And as you probably know, hash maps are pretty much in every coding application. They are really ubiquitous. So we had this an ambitious goal, which was, can we optimize a hash function, specifically of a popular library, which is called AlphaZero flat hash map. So if we target that particular hashing function used in the hash map, then all the programs that rely on this library would benefit. So how can we adapt the assembly gate to hashing? We are very lucky that the definition was very general, so there are very few changes. The main changes is in the definition of correctness. In sorting, we define correctness by having an algorithm that takes a list of permutations and sort all of them, right? We can guarantee that the algorithm is correct. We don't really have a definition of correctness in hashing. Instead, what we measure the quality. And we measure the quality based on the number of collisions after running the hash function. So we start from an arbitrary input distribution. We generate a hash algorithm. We hash all these inputs, and then we say, okay, how many collisions do we have? And so what we do, we optimize for number of collisions and latency. And the good news is that the latency benchmark server that Dan talked about is exactly the same. Nothing changes. The second change that we did is about the instruction set of assembly instructions that we allow. So for instance, we add things like rotations and base shifts. that are not very useful for sorting, but for hashing are quite necessary. So with these changes, we run hashing on, we run AlphaDev on the hashing function of AlphaZero, and it discovered like a faster hashing function specifically for hashing strings from 8 to 16 bytes. So what you can see on the left is the previous version, where the mix function is called twice. So that performs 2 multiplications. While if you look at the discovered algorithm, it only does 1 multiplication, and it does a very interesting operation. It does a rotation on the low bytes by 53. So that's a very interesting operation, because once, this is an operation that wasn't there before, and 2, what I found really interesting is the number 53, because it's not something that we added, right? AlphaDev could come up with any number, and it chose particularly 53. And the other number that it kept picking was 11, which is the complement, because we have 64 bits here, right? And we tried to understand a bit more why 53. And I think our intuition is because it's a really good number of mixing the low and high bytes. Also, of course, an odd number here. But then we don't have a theoretical answer of why 53 is really good, which was, and everyone found this very, very interesting, especially like assembly expert that started looking at this. And it's something that it's very difficult for humans to see this type of optimizations. But then an AI agent can really find this type of optimization, which is great. So to take a step back and look at the overall algorithm, the part that we modified is specifically between 8 and 16 bytes. And we replaced these 2 mix with our new version. And similar to sorting, it's not very easy to make a change in an open source library, especially libraries that are used by many, many clients. And the challenge here is the fact that you cannot guarantee correctness, right? There's no definition of correctness. And every client has a different need, right? What we wanted to demonstrate is that our change would benefit everyone. And we are lucky that there are some tools like Smasher that allow to really benchmark these hashing functions over many different inputs. Also, AlphaZero has some internal benchmarking. And this was very necessary because given a different input distribution, AlphaDev finds a different optimization. So we really needed to be careful with the initial input distribution we would choose in order to make sure that the hashing function would be robust and quite generic and good for most use cases. And we're very happy to say that the hashing algorithm has been accepted. And we observed about 30% latency improvement compared to the previous one, which is huge. We conservatively estimated that this is called more than 1 trillion times per day. And as far as we are aware, we think it's the first time Arela has been used to optimize this part of the library in AlphaZero. And the most important point, though, is that we show that we can generalize AlphaDev to different algorithms, which is great news for us, right? And it allows also to take a step back and reason a little bit more about what type of algorithms can we optimize with this approach, right? Because we observe 2 conditions. One of the 2 is important. The first one is exhaustive verification is possible. Like if you look up to SOR 5, it was very easy to check all permutations. And that is great. If you can do that, then AlphaDev can really suit this type of optimization. However, if exhaustive verification is not possible, like if you want to optimize a very large N for sorting, it becomes a little bit challenging, right? Some approaches are possible, as mentioned, like maybe you sample, you build a permutation adversarially, and so on. But I would say maybe this approach doesn't really suit this type of algorithms. There is another set of algorithms where exhaustive verification is not possible, but it's not critical. And rather, the quality is what we care about. And hashing falls in that category. And we are lucky that there are quite a lot of algorithms that fall in either of the 2. And this can be from cryptographic hashing to serialization algorithms to lossless algorithms like ZP and so on. Cool. So how does this work compare to previous work? Of course, there's been a lot of work in the literature in program optimization and program synthesis and so on. And in our paper, we do a more thorough comparison. I would say that the main difference, especially there's been a work in assembly optimization, RL as well, and deep learning. So in all these areas, I think one of the main differences is that we optimize end-to-end for latency. Often different work optimized for program length, or maybe they assign a cost to each instruction. And these approaches are not always optimal, especially in modern architectures where there is things like instruction parallelism. So it's really hard to predict when instructions can be executed at the same time. While if you optimize directly for end-to-end latency, then we don't need to take that into account, and we really can target a specific architecture. And what allows us to optimize directly, of course, optimizing for latency is very expensive and is very noisy. What allows us to do it is building like this very efficient, almost noise-free macro benchmarker, and having this latency value function. So having a learned model that as we search for programs, it gets better and better because we train this latency value function with the programs that we find. So that I think is what distinguishes us from other approaches. So what are current limitations that we have? Like quite a few actually, because the first one is that we still don't support all algorithm structures like loops and recursion. There is no particular challenge in this. It's mainly engineering. Of course, once you add the loops and recursion, then if you try to measure latency, then you're going to build lots of programs that never terminate. So you need to be careful about that. Also, we might want to rethink a little bit how we represent the programs, like in terms of learning, in terms of the agent architecture, just to make this concept easier to learn. But it's no big challenge. On the other hand, I think what would be very, very interesting is to optimize on the SIMD space. So SIMD is the vectorized instructions in assembly. This is something that is quite difficult for humans to write, especially very efficiently. And I think an approach like AlphaDev can be very impactful in this area. And finally, the third limitation is that right now we optimize for assembly, which has many advantages, of course. We can find very specific optimizations. But if our goal is to deploy to open source libraries, there you don't deploy assembly, right? We always have to reverse engineer to C++. So if our end goal is to have like a function in a higher level language, maybe optimizing directly in the space would be better. So in terms of next step, like what could we do here? Well, when we looked at baselines, we saw how in some cases stochastic search is better, especially when it searches over a local space. So maybe we can combine both approaches, right? You can think of something like AlphaDev come up with new algorithms, and then we apply some stochastic search to search within the small space, right? To find the most optimal solution there. And so combining these two approaches could be quite impactful. Second, of course, language models have shown quite a lot of promise with code. They become really good. So it could be used as an initial prior. And what I really would like to see is some planning capabilities on top of that, right? So what I really mean by that is having a value function that predicts the future. So one could think maybe to have a value function at the token level, or even better, the sentence level or snippet level. So you have a language model that comes up maybe line by line, and then you have a value function, maybe like you can imagine this an MCTS search. And then you have a value function that predicts, which one of the line is going to be more optimal to optimize for latency correctness. And I think that planning capability is what really allows to discover novel algorithms. And finally, I would really like to see the optimization of the entire computing stack all together. Like in our team, we've done quite a lot of work, maybe using AlphaZero to compress videos on YouTube, AlphaZero for resource scheduling, and also memory allocation XLA, and now program optimization. My dream would be to see, like, can we tackle all these problems all together, right? Can we optimize both software and hardware at the same time? And I really would like us to get there at some point in the future. So in conclusion, AlphaDev discovered faster sorting and hashing algorithms from scratch. And I'm really happy that we didn't stop at the simulation. We didn't stop just at the benchmarking step, but we went all the way and we deployed these algorithms to two open source libraries, and now they're used more than trillions times per day. Also, I'm really happy that it's another victory for reinforcement learning outside of the gaming domains, right? Often reinforcement learning gets a lot of critics saying that, oh, it's great in application in Go or chess and so on, but what about real world applications? Well, this is another one. And I think it shows also that there is a lot of opportunities in the space of program optimization. So this is the end of the talk, but feel free to reach us by email, and also feel free to ask any questions. We're more than happy to answer this. Thank you very much.
Thank you, Andrea and Daniel, for this very interesting presentation. I wanted to start with something because, in philosophy, often it's realized that people talk about different things using the same word, and that can lead to a lot of discussion that we'd like to avoid. And in this context, I wanted to raise the point that, in the newspaper these days, we read a lot about algorithms in social media, for example, predicting the next post on a social network, the next video on a video website, etc. But this is not the type of algorithm that we're talking about here, right? Or do you see a distinction here, or can you maybe clarify as experts on algorithms what falls under an algorithm and what does not?
That's a great question. I think thinking about how I would define an algorithm, it's you can look at it from the coding level, where it's a piece of code that receives as input something and performs a function and then produces an output. You can also think of it like from a reasoning perspective, that it's you feed in a question, for example. It then answers the question and gives you a suggestion or an answer if it's definitive. And so I think that there is also, I think thinking about algorithms in that way allows you to sort of also reason about these sorting and hashing algorithms that we discovered, in the sense that these algorithms are more like, here's an input and we need to get an output, where it's like, here are some unsorted numbers, sort them for us, or here is a string, turn this into a hash. And I would differentiate that from an algorithm, for example, in a social network, where it's asking more of a question. For a given user, what does this user like, or what should be recommended to this user, for example.
Okay, thank you. That's a very useful and usable way of thinking about the two concepts. I wanted to go back to just you were talking about the two types of algorithms that you've looked at, so sorting and hashing, and you already described a little bit in one way they're different. So sorting has an objective measure of correctness, and with hashing it's more statistical, like you see how many collisions there are. So is this how we should visualize, or how we should understand algorithms? Like, either these sort of, can you describe all types of algorithms, let's say computer algorithms, in these two categories? And was that the reason you chose them, because they're different, or rather because they're similar, or why did you choose these two types?
Yeah, so I would say that one of the reasons the reason we chose sorting initially is because we wanted to find an algorithm where we could exhaustively determine whether or not it was correct, and we knew that if we start with something like sort 3, we could do that. And then once we sort of started to understand the space, we started to think about, well, are there other algorithms out there that have properties that are maybe slightly different from sorting, that don't need exhaustive correctness, that we can still tackle? And this is where we came across hashing functions. And I think something that's really interesting is that there are algorithms you can learn that are very general, in the sense that they should be able to serve any application or any user request. And these are the types of algorithms we chose. Sorting is in an open source library called by millions of applications, billions of users. And the same for hashing, same kind of concept. But now, in many cases, you might have maybe in your company, or you might have a particular app, for example, that has a particular distribution that is different from sort of just being able to accept any possible sorting values that are in a different order. You might find that maybe you have a setup where you call sorting, but often the first 2 numbers are sorted, and you only have to worry about the rest of the numbers. And in that case, what we found is that AlphaDev is very good at looking at the distribution and saying, I'm going to build something that's very specific to that distribution. And this is something where we think there's going to be very big gains possible, is if you're able to look at algorithms, not so much from the general perspective, but by focusing on a particular distribution based on your product, based on your company, we think that very big gains are possible there.
+1, and on the look at the input distribution is one way, but also the architecture that we target. When we optimize the end-to-end for latency, that takes into account both the input and the architecture. When we put these algorithms in the open source libraries, we had to benchmark across all different type of architectures to make sure that the speed up was across all of them. But if you have to run your software on a particular target, then you can really optimize for the target, right? There are some architectures that are very efficient at some assembly operations or can really take advantage of some other operations. Then AlphaDev can really leverage those. So I think that's a very nice property of optimizing end-to-end.
Okay, thank you. That makes a lot of sense. I wanted to jump back to a previous speaker, a colleague of yours, Hussein Fauzi, who spoke earlier this year at AI for Good on his research, which was also published in Nature and has a similar name, AlphaTensor. That discovered a faster way of matrix multiplication. So how is this the algorithm that you're working on is an algorithm specifically used in computers, and that's an algorithm in mathematics maybe? How is that different, and how did that lead to different softwares that you developed for this?
Yeah, so I think the way to look at it is they have sort of the same underlying ancestor, which is AlphaZero, or same underlying fundamental algorithm, which is AlphaZero. And where they really differ is in the types of games that they play. So in the case of our setup, we play the assembly game, where the goal is to add assembly instructions together and to generate an algorithm. In the case of AlphaTensor, the game is to build a set of matrix multiplications that allow you to multiply matrices more efficiently. And so the games are different, and then also the way in which you reward these systems are different. So in matrix multiplication, you would reward it by the number of operations that need to be applied to multiply matrices. In our case, the big, I think, differentiating factor is that we had to optimize for actual measured latency, because especially when we got to the case of there being branching in these variable sort algorithms, for example, you couldn't optimize for the number of instructions. And so there it became very important to optimize for latency. And so there are these types of games that are played, the rewards that are gathered, all led to having different ways in which we approach the problem. So, and how we also then adapted AlphaZero to each of these problems. And I think the representation is also, of course, a different area, where for matrix multiplication for AlphaTensor, they needed to be able to get AlphaZero to understand the structure of matrices. And in our case, the goal was to understand the structure of assembly algorithms.
Okay, very good, thank you. And that actually leads me to a follow-up question. Because, as you said, there's a kind of common ancestor, AlphaZero. So if I understand it correctly, following as an outsider interested, there was AlphaGo that was trained on the game of Go, using many historical matches, databases, etc., the rules, etc. Then there was AlphaZero, which was taught the rules, but not given these historic matches. And then there was also MuZero, which was not given the rules or the constraints of the game, and had to find them out. That system discovered the rules itself. So how come you, and I guess also AlphaTensor, but the question to you here, for AlphaDev decide to go with AlphaZero and not, for instance, MuZero, a more relaxed system yet?
Yeah, I think AlphaZero, like if you know the rules of the game, then you can leverage that, right? MuZero is often very useful in situation where if it's not just you don't know the rules of the game, but like it's either very expensive to run them, or like it's not something that you have access to. If you can leverage them, absolutely. Like if you can add that prior information, you should. In terms of we switched to MuZero for source 6 up to 8, and that was more of a computational efficiency reason. And the difference is that when you do Monte Carlo tree search, like in AlphaZero, you actually run the environment, while in MuZero, you're in the latent space. So if running the environment becomes quite expensive, like in our case, it means running the assembly algorithms on all permutations. So that means when they become a lot, like we couldn't scale with that. Then we says, okay, you know what? Let's do it in the latent space. Let's have a learned model, and then let's do the MCTS search over the space. So I would say, like if you have the information, you can run your environment quite fast. Go for AlphaZero. In the situation where it becomes a scalability challenge or we don't have that information, then MuZero can help us.
Okay, excellent, thank you. And that brings me to a question, I think, quite naturally of one of the participants of today's webinar, Lucas Teixeira. I think that's a Portuguese name. I hope I got that more or less correct. And his question is this type of endeavor possible for companies without access to large clusters? So you just talked about how computationally expensive this can be, and of course that you then, so what are your thoughts?
I think these are excellent questions, and it's always a question about trade-offs, right? In the case of one reason we decide to target sorting and hashing is because they're called trillions of times per day. So like if we're able to save like a percentage of those, then the computational cost of discovering faster sorting and hashing algorithms is very minimal compared to the cost of discovering them. In our paper, we reported all the cost of running these algorithms and how it scales. So it's really a question of trade-offs and looking, okay, how expensive, like how often do we run this function, how expensive it is for us, what would be the benefit of like saving, I don't know, X%, and does it make sense for us, like to spend these resources in order to try to discover a faster one?
Yeah, and I think in general for, if you want to start up and, like the latency benchmarking server was something that, took quite a lot of engineering work to put together, but that doesn't mean that you can't begin by saying, well, let's try and optimize for program length, branchless assembly programs. And there are many of these. And another thing that we mentioned in our paper is you could also imagine taking a very big function, but looking specifically at the logic component of the function, and then fixing everything else and just trying to optimize that logic component. And this is another way in which you could do this, where the idea is, if you can reduce the number of programs, then you could have gains there. So I think there are also innovative ways of being able to do this without having to build this massive benchmarking server, for example.
That was actually, we have an expression in Dutch, is that you mowed the lawn in front of me, and I think that's more or less what you just did, because I was about to ask a question, but I'm going to try to ask it anyway, because maybe there's a bit more to it than but it's something you probably already answered it. If I understand it correctly, in one of the cases, the innovation was to delete one line, MOV RDX, RCX. Couldn't you discover this empirically, like commenting out line by line? I mean, there are 30 odd lines, right? Comment them out one by one. That's what you just said. Yeah. Is that correct?
Yeah. So I think that definitely one approach is to try and analyze it yourself. One of the things that's very difficult in doing that specifically is, you need to have a lot of assembly expertise in order to be able to try and find these discoveries. And I think one of the things that, I think there's an advantage and a limitation. I think there are some functions where you might be able to look at them and say, oh, this is one way in which we could manually do this and we could improve it. And there are many very, very talented people that are able to do something like that. And then there are other setups where by learning something completely from scratch, it allows you to also look at very different structures and potentially not be biased to the structure that currently is the best structure. So like with the variable sort, for example, we gave, there's sometimes this benefit to being able to say, well, let's start from the beginning and then try and build something from scratch. So I think there are these different settings, and I think this is where it comes down to choosing the right function based on what you're trying to do and what you feel you've got the resources to do. But I think both of these approaches are very impactful, regardless of which one you tackle.
And in the case of sort tree, like we show that in our paper, we show that approaches like stochastic search can find that optimization. But we notice the benefits of something like AlphaDev coming when the space of solutions becomes increasingly complex, especially things like hashing. The space is massive and is highly dependent on your distribution. In the case, an approach like AlphaDev really shows its full potential.
Okay, that makes a lot of sense. Maybe a slight follow-up question, and maybe that I read a blog post by a person called Justine Tenay. I hope I said that correctly as well. And in her blog post, she says that there are 2 more MOV operations that can be removed. Maybe you saw this post, or maybe not, but is that something, did you think about this, or is this something?
When you say 2 more modes of operations, what do you mean exactly?
Yeah, I'm afraid I don't know all the background. Maybe that's I'll have to maybe follow up in writing on this question, but I can recommend anyway to look at this post. The question basically is that they said there's some slack still there's still some things that can be removed. Do you think that's indeed the case?
Absolutely. I think like what we do, and we specify in the paper, is that we choose a set of assembly instructions, and then we do a search over that. We never can guarantee that this is optimal, of course, and especially if you think of something like hashing, our goal is to hashing, the space is extremely large, right? I'm pretty sure there are so many optimization on top that can be done right here, right? And one thing that is important though is one, optimizing for speed, because what we notice is that program length is not always correlated with speed up, right? And in the case of sorting, like you can come up with many quite neat tricks, quite cool tricks in order to reduce the length, but that doesn't lead to a speed up. And the second problem is that if you want to deploy this to an open source library, which should be the goal, right? So everyone can benefit from this. It needs to be possible to reverse engineer to C++. So many of these tricks, like for instance, a few of them depending specifically, I think, on the address location or things like that, is very, very cool. And I think it's very neat. But then it's important that we are able okay, can we come up with now a program that we can deploy to a library and then can be used by every program out there. So that should be the final goal.
Okay, very good. Very clear, thank you. I want to step back a second. And let me just quickly see if I can share my screen here. 1 second. So this weekend I was with my daughters in the Amsterdam Kids Science Museum. And of course, I was already thinking about our discussion that we were going to have today. And they have this here. And now there are 2 panels missing, but this is basically the way they summarize the history of science for kids. So it starts up with astronomy in the bottom left, and then the wheel, invention of writing, geometry, etc., and Pythagoras there, the Hippocrates of Kos, and then ends with the printing press and the Cabra Oscura. And in between there, you see Muhammad al-Khawirzi. I hope it's correctly as well. So this is the person that the word algorithm was named after, and it is apparently this fundamental. And that this, there are maybe 12 or so things depicted here for kids to learn what science is, and apparently algorithm is one of these such fundamental concepts. So, what do you think? Is algorithm really so fundamental, and are there more things that we could be understanding as algorithms that we're currently, used to thinking in different ways?
Yeah, I think, I mean, firstly, it's great to see those kinds of exhibitions. And I think there's, with algorithms, the way in which algorithms evolve, I think is, through someone discovering, a new innovation and a new way of thinking about it. And then there tends to be, on top of that, more and more improvements. And sometimes there's sort of a fundamental breakthrough, and sometimes there are these iterative improvements. And I think, one of the goals that we really wanted to have in this work is to kind of give the message of it sometimes can be really beneficial to start from the ground up and rethink it and see if there are different ways of designing algorithms, because algorithms really sort of underlie all of the things we do, even from the way we think about things. There are, if we want to do something, we, make a cup of coffee, we have an algorithm that says, well, we should walk to the kitchen, pour the water into the cup and make the coffee. And so I think that being able to sort of constantly think out the box, ask different questions about algorithms that might, seem well understood and there's no way to improve them, I think is really a good way for us to, as a sort of society trying to improve algorithms, to try and approach it.
Okay, that's very interesting. You mentioned that about the cup of coffee. That's exactly kind of the example that was given in the Kids Science Museum of an algorithm as a recipe on how to prepare a meal or a cup of coffee in the same trend. And then, so when I was looking more at the history of this word algorithm, I came across something else, and I just wanted to share that with you as well. So in one of the articles I read about algorithm as a concept, they mentioned that it's a very recent word that basically was not used, and I didn't believe that really, so I looked it up. And it's true, actually. So if you type up n-gram, this shows you from Google, how often is a word used percentage-wise in a book, of all the books published in that year. And basically, the word algorithm doesn't exist until the 40s, 50s, doesn't take off until the 60s. And then also interestingly, from like 2000 or so, it falls quite a lot. And I thought first, well, that's maybe because people that talk about computer algorithms talk about it on the internet, right? Don't write books anymore. Could be. So I looked at the internet version of this, which is Google Trends, and it's also falling here quite a lot. So we see that currently we're at, let's see if I can get this to show, 17% of the high point around 2005. So do you know what this is about? I mean, I guess this is a very weird question, but why is the concept algorithm less in vogue than 20 years ago?
I think it's a great question. I mean, I think that if I had to guess, maybe some things affecting that is, as different industries evolve, I think the language used to describe new innovations sometimes is a little bit different. So maybe if you think about like neural networks, I imagine like the usage of that has increased incredibly. And then people, when they talk about different neural networks, often talk about different neural network architectures. And these neural network architectures are essentially emitting like a different algorithm in many cases. But I think that maybe what's happening is that these other kind of new up and coming terms are sort of being used in place of them, which might explain the last 15 or so years of that happening. Maybe.
Okay, that makes sense. The one thing that I could come up with, but I don't know if it makes sense, is maybe these algorithm development in C++ standard library reached a level of maturity that maybe there wasn't just not so much discourse anymore. And maybe now with your new approach, there is, turns out there's new ways of making improvements. Okay, we have another question from Steve Jessup. How portable are these optimizations in terms of different CPU architectures? So I think, Andrea, you already mentioned it in your penultimate slide. So ARM and x86.
Yeah. Excellent questions. So during training, we mainly targeted x86, but then when we wanted to deploy to open source, we run benchmarking all of them, and in the commit, people can find the performance benchmarking all of them. We showed improvement across all of them, so we're happy to see that it's quite portable, and in a sense we're almost lucky that it was portable across, and then otherwise we probably would have to change the benchmark, make sure that we target directly during training on all of them. But then yes, it's a really good question, and I don't think it will always be the case. I think it depends on the type of optimization and the type of instructions that we allow to search over.
Okay. Oh, okay, excellent. And actually, that brings me back to another thing that you mentioned at the end of your your joint presentation. This SIMD. So these vectorized instructions. That's something that you think is very good. So what will that look like? What will research in this area for you? What do you intend to? How do you intend to take this forward in that area?
So I think in terms of taking it forward, that's still a question of what is how to take it forward, because as Andrea was mentioning at the end, there's this question of also do we want to try and generate the code at a higher level language versus do we want to go and attempt to do SIMD? But I think this is where the general community can help with this goal or this vision, because I think we see a huge opportunity to optimize SIMD instructions using AI. And SIMD is particularly difficult to understand and to make sense of because things are vectorized, things happen in parallel. And as a result of that, this is where we think there are a lot of suboptimalities that exist. So if there's anyone on this call that's working in that space, we would highly recommend looking into SIMD.
Yes, and also SIMD, you can target SIMD at different level. One can optimize SIMD directly at the assembly level or at higher level language. What is the right level of abstraction that we should target? I think is still an open question. And similar, what type of algorithm we can target. I feel like there is a lot of work and opportunities in this space.
Okay, excellent. I realize that we're already well past time, but I wanted to ask one final question. So in your example with the sorting, you look at integers. We can of course also talk probably about what else is possible, but I also had a question about like the consequences of this. So integers are of course used a lot in cryptography, and cryptography relies on these one-way functions. So like squaring the number 5 is easier than finding the square root of 25, for instance. Now with this sorting that specifically you've done for integers, is it something that could risk cryptography in the way that we know it? Of course, there are other risks already, but are there consequences like this that you think are could happen if this continues to go forward in the way that we've set out?
I think that taking a step back, if we look at how the process that we followed in order to get these algorithms used, like in these open source libraries, there were very stringent processes that had to ensure firstly that it worked, as Andrea was mentioning, across all architectures, that all possible edge cases were taken care of, that there was just basically, these were very solid algorithms, and this 3-month process where there were human reviewers that were back and forth with us saying like, write a test for this, write a test to check that, made it almost foolproof in the sense that if it when it was accepted, there were a number of people that were convinced that this was totally fine. And so I think so long as we go responsibly and we continue to really look at these new innovative solutions that are coming out and really scrutinize them in the right way, I think then we can mitigate that risk to a large degree. So that's hopefully how we can continue.
Okay, great, thank you. There's one final question that just came in. Let me see if this is really quick, or maybe just give 2 words about it. Bas Kramer, could AlphaDev be effectively used for neural architecture search?
I think that in general, reinforcement learning is very good at doing parameter searches, and AlphaDev has been built in a particular way to build assembly programs. But I think if we go back to its ancestor AlphaZero, or for that matter any reinforcement learning algorithm in the space, there's many open source ones available as well, I think that you could certainly use it for neural architecture search. You'd have to change the game in a sense, where now you want to find the set of parameters that will lead to the best model or architecture that you're learning. But yeah, I definitely think it could be useful.
Yeah. And I think it would be a really good application, especially when we care about multi-objective, right? Maybe here you care about the size of your architecture, or like how you can partition it on your hardware. So like you can fit a larger model on the hardware that you have, but at the same time you care about performance and execution time, and all of these could be rewards. And reinforcement learning can balance that really well, like that really long-term planning.
Okay, well, great. Well, thank you both very much, Daniel, Andrea. It's been an absolute pleasure. Sorry for taking more of your time than we said we would. I think it was just too interesting, and we had to ask more, me and all the participants today. And we wish you all the best with the continuation of this research, SIMD, higher level languages. I think there's so much to be seen, and we look forward to seeing that being published, and hopefully you will be available to tell us more when the time comes.
Yeah, definitely. And thank you so much for having us. We had a lot of fun.
Thank you.
Great. Thank you very much. Back to Anna then.
Thanks. Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.